All right, good morning, everybody. Thanks for being here on a rainy Friday. Let's jump into it. We're going to continue the cerebrum today, continue with the brain. We're going to wrap the nervous system up, if not today, by Monday. We'll do a short unit on the endocrine system before break, and then we're going to cover cardiovascular and respiratory systems in the last couple of weeks of class. So with that in mind, our agenda today looks like this. I want to just quickly review one of the questions from Wednesday's Tick It Out. I've got a human anatomy in the news for you, which is actually a really cool story that just came out a couple weeks ago. I'm excited to share this. I'm going to finish up the cerebrum. We're going to watch a fun video about a guy who got a rod blasted through his brain. And then we're going to talk a little bit, if we have time, about the protective layers of the brain. So the meninges, the skull, cerebrospinal fluid, etc. I want to quickly debrief exam 2 that you completed earlier this week and give you some information about your next upcoming quiz. And then, of course, we've got a Venn diagram to wrap things up on a Friday. No Tick It Out today. So before we dive in, questions? I knew if I waited long enough, it would work. Okay,
I had this process.
Yeah.
Is there another exam before like the lab practical, or is the lab practical like the next big thing?
Yeah, so you have, the course has 3 lecture exams and 2 lab practicals. So your last lecture exam will be the last week of classes. I haven't decided exactly when or the format yet. And it will probably, well, it will be then. I'll let you know the format as we get closer. The lab practical, remember, will be during your allotted final exam time. It's on a Tuesday morning, I believe. It's on the syllabus. I don't remember exactly what the time is. I'd like to do it that way because that 3-hour chunk, we don't need that for a lecture exam, but it's actually really nice for the lab practical, for setup, and to make sure you have enough time to do everything and that kind of thing. So, does that answer your question, Holly? Good one. Other questions? All right, so on Wednesday on your way to class, I asked you this question: what structure will you find just dorsal and inferior to the thalamus? And about 2/3 of the class got this right. It is the epithalamus, but I just want to make sure you've got this. So remember, the diencephalon is composed primarily of the thalamus you see here. Then we've got the hypothalamus, which is kind of rostral and inferior. And then remember, you've got your pituitary down here. And kind of in the back, more or less in the back, a little bit inferior, we have the epithalamus. And of course, that is important. And also, well, I don't have it labeled here, but the pineal gland is on there as well as part of the epithalamus. Just a quick reminder of that. Sound okay? All right, so human anatomy news. This is a cool story. So the game Pong was like the first computer game. You've probably heard of it, if not played it. Basically, you've got like a paddle on this side that moves up and down, a paddle on the side that moves up and down, and a ball that goes back and forth real slowly, or like a cube, right? I actually remember this game because I'm like 200 years old. Yeah, and it was a big deal at the time because it was the first computer game. It's kind of crazy to compare it to, like, I don't know, Mario Kart or something like that now. But what is been really interesting is this past well, this just it was the research happened over the past couple of years, but the story just came out the past couple of weeks. Scientists took human brain cells. They laid them on this little microplate that interfaces with electronic circuitry. So this thing is a blow up, but it's about the size of a thumb. You can see all of these axons going across here. And they taught these brain cells in this dish to play Pong. So there is about 800,000 cells. And so this is smaller than the brain of a cockroach, for example. And they're linked to a computer. And what they did is they taught these cells to learn to sense the position of the ball and then to control the paddle to make the ball bounce, right? And so here's a quote from one of the researchers. It says, if we allow these cells to know the outcome of their actions, will they actually be able to change in some sort of goal-directed way? And the answer was yes. They weren't super at Pong, but they could play it well enough. Better than random chance for sure. And what they did is cells really like predictability, nervous cells especially. They really like to know what's going to happen. And so they train the cells that if they move the paddle and bounce the little ball, that they would receive like this kind of regular electronic pulse, like a burst of electronic activity that was kind of simple and predictable. But if they messed up and the ball got by the paddle, then they got this like stream of white noise, and the cells really didn't like that. So they basically like kind of organized themselves and figured out, all right, we don't want this white noise. We want this like good stimulus. And so they were able to move the paddle in a way to block the ball to get that reward, let's call it. As I said, this is less cells in the brain of a cockroach, and they weren't perfect at this, but they were pretty good and they could actually learn. So this is really kind of exciting research in thinking about the future of electronics, which is going to mesh like traditional electronics and potentially living cells in a way that can increase capability. And the reason for this is computers are really good at doing simple things that we can tell them to do directly. If you give them a set of tools and a set of instructions, they can do things, and they can do things super fast. That's why computers are so good, for example, at math, right? Because there's a set of rules, there's things that needs to be done, and you do it, computers can do it. Humans, on the other hand, maybe can't do that as fast, but we're really good at creatively figuring out problems. And the example that they talk about in the article is, for example, making a cup of tea. If you give a computer a very set, like put the tea box here, put the boiling water here, put the teacup here, tell it how long to do what steps, a computer can learn to do that really quickly, right? And so can you. Now, if you go to your friend's house and you want to make a cup of tea, a computer is going to be lost. Whereas you can rummage around in the cupboard, you can find a teapot, or maybe there's not a teapot, so use a saucepan to boil your water. Maybe there's not a mug, but so you can use something else. Like, we're good at making a cup of tea, even if we don't have everything exactly laid out in front of us as we need. And that's where computers aren't so good. This kind of interface, though, obviously it's very simple now, but someday could maybe be used to solve those more complex problems. I was really fascinated by this research. Given that we're on our brain segment, I wanted to share that. And so I think this is a minute long. I'm going to show you a video of the brain playing Pong. Or excuse me, not the brain, these cells playing Pong. It's not exciting. I'm going to put the disclaimer here, but it's pretty fascinating to watch how it moves. Let's see if I got some sound in here. Oh, shoot, sorry. And so they actually simplified the game. Normally there's a paddle on either side and you're playing against each other. They just had it bounce off this wall so that they can control the paddle here. But those little brain cells are actually steering that paddle, trying to get it to bounce that ball back. You can see them kind of moving around. You can see it's kind of jittery. Go, 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 yeah. So 800,000 brain cells on an electric circuit board. That was a good move, right? Have any of you ever played Pong before? Yeah, okay, cool. Yeah, so you can expect a question about this in upcoming quizzes and exams. Generally, I've been putting multiple choice questions on your exams. You've seen them. I have a link to the original scientific article as well as the popular press article in your program. As usual, you don't have to read the original article, but I do recommend reading the popular press article. It's short. I think it's from the NPR website. It'll take you 5 minutes. It's a fascinating story. Did anyone hear about this in the news this past week? Bless you. Questions, comments, thoughts?
I'm kind of confused.
Mhm.
How do they control like the thing, like where were the cells?
Yeah, so the cells are plated on. Whoa, just going backwards in the video here. Hold on, let me go back in the slide. They're plated on here, and they can receive information about where the paddle is and where the ball is. I don't know exactly how that works, but it's basically coded electronically. And then they can send electronic signals back that will then move it. So the cells don't actually see what we're seeing, but they can sense it through electronic signals and respond accordingly. And then we just get this visual output so we can kind of see what's going on. Does that make sense? Yeah, that's a really good question. Yeah, Zoe.
Isn't it their learning or? Because I know that they're using like the like negative feedback kind of thing with the electrical signals.
That is learning though, right? Just a simple, yeah. I think the answer to that question is yes. They're learning through that conditioning process. Cool. All right, let's get back to the cerebrum. So this is the adult brain. I'm going back to this a bunch of times. We're on the last major section of the brain, the cerebrum. You've got a study guide. The QR code is there if you need it. It has diagrams, et cetera, et cetera. I want to just pick up right where we left off last class and talk about the primary sensory areas. So remember, we have sensory areas, we have motor areas, and we have association areas. I'm going to walk through each of those in a little more detail and specifically get into some of the specific sensory, motor, and association areas. So the somatosensory area is where signals are received related to touch, pressure, etc. The visual area is what processes sight, and that's in the occipital lobe. Auditory processes sound, which is in the temporal lobe. Vestibular is in the insula, and that's what processes our equilibrium. So that's also information from the inner ear. Gustatory is taste, is in the insula. Just as a reminder, the insula is this lobe that's deep to the temporal lobe here. You kind of have to pull it apart at that deep sulcus there, and you can see the insula lobe underneath, deep to the temporal lobe. And then finally, the olfactory, oh no, two more. Olfactory lobe is in the, olfactory sensory area is in the temporal lobe. And finally, the visceral sensory area. So that deals with pain, pressure, hunger. So this is the information coming from those sensory visceral neurons. So let me talk about each of these in detail. Here's just kind of a list of the general, the major areas and where they are. But let me dive into this in a little more detail. So first, I want to talk about this somatosensory, the primary somatosensory cortex. You can see here that I note that it's on the anterior edge of the parietal lobe. And so let me just show you where that is. So this is anterior or posterior. So this is the face is looking down at the ground in this case. And we have the parietal lobe, which is posterior to that postcentral gyrus. So this is the part of the parietal lobe that is kind of closest to that postcentral gyrus. So it's the forwardmost part of the parietal lobe. And here, this is where we process information from our somatic senses. And it allows us to, so what's interesting here is that there's different parts of this area process information from different parts of the body. And we can kind of map those parts of the body onto this area. Noting here that this projection is contralateral. So on the right side of the brain, we're processing information from the left side of the body and vice versa. Now, the way that we map where in our body we're processing information onto this postcentral gyrus, this somatosensory cortex, is I shouldn't say not onto this. It's not on the gyrus. It's, well, no, it is. You can say that it is located on that postcentral gyrus. We map how information is received from the body onto this area through something called a homunculus that looks like this. And I always find this really, really fascinating. So this is that somatosensory cortex kind of in a coronal section here. And you can see how the body maps onto here. And what's really interesting is that the size of the structure relates to how much sensory input you're processing. So for example, we are processing a lot of sensory information from our face, our lips, our eyes, etc. here, although, well, this is like sensory information around the eye area, not the visual information specifically. We're processing a lot of information from our hands, but we're processing relatively much less information from like our body, our head, our neck, our knee. We got a little more on our feet and some on our genitals, of course, as well. But you notice that this body shape is disproportionate because we get a lot more sensory input, especially from our hands and face, than, let's say, for example, from our torso. And this is because we have more fine inputs from these areas, essentially because input from those areas is more important for us than it is from other areas. So it's not really that important that you can, for example, have a fine sense of touch, let's say on your lower back compared to on your fingertips, right? For the tasks that we perform. Now we have a similar homunculus for our motor output that I'll show you in a minute, but I'll start with the sensory input. And what's interesting is the motor output and the sensory output are kind of different. There's places where we receive a lot of information, but we don't give a lot of motor output, and vice versa. And I'll contrast those in just a second. I want to show you where this is on the brain. So the primary somatosensory cortex is right here. It's the anterior most ridge of the parietal lobe. Sorry, I just want to see what I've got here. And then just posterior to that, we have this somatosensory association cortex. Of course, that's where information from a whole different number of different places are integrated. So that information is first received and processed here, and then the information is integrated in the somatosensory association cortex. Let's see here. What's important to note is that in this association area, we're integrating information not just from our current sensory input, but also from our past experiences in our memory, right? And so it's not just, if you're recognizing an object, you're not just looking in the immediate sense of the input you're getting about that object. You're also making connections between that sensory input and things you've experienced in the past. I think that's all I want to say about that. So we've got the somatosensory cortex, primary somatosensory cortex, and then the somatosensory association cortex, which is just posterior. Next, we have the primary visual cortex. This is located in the occipital lobe. Way in the back here, you see just superior to your cerebellum. This is what's important to note here is that this is the first area where visual information is processed, but visual information is actually processed in a number of different places. So this is the largest sensory area related to vision, but it's not the only. It's the largest and first, but not the only. That's a good way to say that. And here, our processing is contralateral as well, meaning information from your left eye is processed in the right lobe of right occipital lobe, and vice versa. Of course, in association with the primary visual cortex, we have the visual association area, which is just anterior to the primary visual cortex. And here, as you would guess, we're integrating that visual information. And so we're integrating ideas of color, form, movement, texture, etc. Well, texture can be both visual and touch as well, but texture, etc., etc. Note that this area extends a little bit from the occipital lobe into the parietal and temporal lobes. So it's kind of bridges the parietal and temporal lobes there. So primary visual cortex, visual association area, occipital lobe. Next, we have the primary auditory cortex, and not surprisingly, I'll just talk about it at the same time, the auditory association area. So again, this is where the information is first processed. This is just here on the superior aspect of the temporal lobe. And then that is processed in this association area where that information is integrated with past experience and other sensory input. What I want you to know here is just that primary auditory cortex and the auditory association area, generally where they are on the temporal lobe, and generally what they're doing here. Note that this information is not contralateral. So we're processing information from our left ear on the left side and vice versa. We also have this special little area called I'm actually not sure how to pronounce this name. I think it's the Wernicke area or Wernicke area. This is a special area that's important for specifically for recognizing speech. So I mentioned in class on Wednesday that there are specific areas for recognizing and producing speech. This is the area for recognizing speech and basically decoding those complex patterns of speech. Let me just see one thing before I get into too much detail here. Oh yeah, I've got a couple more sensory areas and then we'll talk about the motor. That's great, actually. We have the olfactory cortex, primary olfactory cortex, which is involved with smell, of course. This is in the temporal lobe as well. And it's part of this group of structures called the rhinencephalon, which literally translates as nose brain. That includes the piriform lobe, which you didn't talk about, don't worry about that in detail, olfactory tracts and olfactory bulbs. All I want you to know here is that there's a bunch of different parts of the brain that are involved in olfactory, your olfactory senses. And what's interesting is that anatomically, these structures are close to something called the limbic system, which is the structures of the brain that are associated especially with emotions and emotional processing. The takeaway message here is these olfactory areas and the limbic areas are very closely connected, which is why our sense of smell has such strong emotional content, right? I'm sure you've been to a place where all of a sudden you smell something that reminds you of something out of your childhood or like your grandmother's house or like, I don't know, any number of places you've been. And you have this kind of visceral response to that because that emotion, that olfactory input carries a lot of emotional significance because those systems are so closely integrated. So they say that smell is the sense that's most closely tied to emotion for that reason. And then I've got one more sensory area for you. That's your gustatory cortex. That is the area that is right up here near the lateral sulcus here on the temporal lobe. And this is involved with processing taste, of course. Oh, actually, there's the gustatory cortex. I forgot I had the vestibular cortex is on here as well. That is in the insula, as I mentioned earlier, processing information related to keeping your balance. And then finally, the visceral sensory area is in the insula as well. So the takeaway here is these two, the vestibular or equilibrium cortex and the visceral sensory area are both in the insula. So all I want you to know from these is know the names of these areas and know generally where they are. By generally where they are, I mean which lobe they're in. And for some of them specifically, I mentioned whether they were contralateral or ipsilateral. So the primary sensory cortex and your primary visual cortex are both contralateral. This is like the whirlwind tour. I mean, you could spend, well, they do spend whole like semesters on this topic. I'm just giving you the kind of broad overview from an anatomical perspective. From a functional perspective, there's a lot of cool stuff going on, but we won't get into it. So those are the sensory areas. I want to talk about the motor areas now. As you might guess, the motor areas are responsible for sending output from the brain, signals to the rest of your body to do stuff. We have here the primary motor cortex is just posterior to this central gyrus here. And we have, where am I going here? No, excuse me, anterior to the gyrus. So it's this precentral gyrus right here. And then we have this premotor cortex right here. And so well, I'll walk through those in more detail. But right now I want to focus on the premotor cortex and the primary motor cortex. So the premotor cortex is where you kind of plan out what you're going to do. So this is where you integrate information from a number of different places and you kind of think, okay, I want to do this task. How am I going to do that? I'm going to go, I don't know, what's a fun thing? I'm going to go grab this umbrella off the wall. So I'm thinking, okay, that's what I want to do. How am I going to do that? Well, first I've got to walk this way, then I've got to walk that way, then I've got to extend my hand, et cetera, et cetera. I've got to watch these stairs. And this is where all of that kind of plan of what you're going to do gets formed. And that's just anterior there to the precentral gyrus. So that's up here, anterior to your primary motor cortex. Next, the primary motor cortex is right there. And right there, meaning just anterior to this gyrus. And this is where that information basically is formalized and sent out to your skeletal muscles so that it does the thing that you just planned to do. So we've got a planning area, and then we've got a doing area. Now, just like the primary sensory cortex, we can map parts of our body onto the primary motor cortex in a way that describes how much brain resources, how many neurons essentially are associated with moving certain parts of the body. And that looks something like this. So this is kind of cool. You can see that again, the face and the hand are large because we spend a lot of our brain energy controlling our hand and our face, and relatively little compared to the rest of the body and the feet. You notice that we had much bigger feet in the sensory here. Let me actually put these two juxtaposed. Actually, yeah, that would be useful. Give me 1 second. I want to make a quick slide here that puts those two next to each other. I think that would be useful. There we go. Okay, I'm just quickly putting those two. Okay, so this is the sensory homunculus. This is the motor homunculus. And you compare, notice that the hand and face are big in both. Notice that the tongue is about the same and actually pretty big in proportion to the rest of the body. Notice that we get the feet are much larger in the sensory cortex than in the motor cortex. Notice, this is interesting, I think, that we have genitals in our sensory cortex, an area that maps onto the genitals, but not in the motor cortex, which makes sense if you think about how those function generally. So that's kind of cool. You can see the difference there in how we allocate our resources to either receiving information or sending out information. Questions? Take a pause there. 2 slides. This one? That's a great question. Yeah, because we use it kind of differently and we use it a little bit independently. That's exactly it. And how big is it in the 2 areas, actually? Let's see. Yeah, it's pretty big relative there. You can see in both of them. That's a good, actually, I never really noticed that before. That's a good observation, Morgan. All right, let's talk about a few other motor areas. We've got the frontal eye field. This controls, so go ahead and look down at your paper, look up at the screen. That area is controlling the muscles associated with your eyes specifically. We also have this special area called Broca's area. That's only found in 1/2 of your brain, interestingly enough. And it is responsible for managing speech production and language. So this is kind of the analog of the Wernicke's area back here that processes speech. This is where we are producing speech. What's interesting is that in our left hemisphere, we have this area. In our right area, we have another corresponding area that it's not responsible for producing the language per se, but rather controls like the emotional overtone of how you say things. So this area, you can think about producing what we say. And in the right hemisphere, the corresponding area produces kind of how we say it, which is, of course, super important for communication. There's probably more information coded in how we say something than actually the words that come out of our mouth. God, you. Does that area have a specific name? Not that I know of, which is weird, right? And actually some of these areas, so just in terms of anatomy, you'll see that there's parts of your body like Broca's area that are named after people. More and more we're moving away from, we're changing the names of things so they're not named after people, rather they're named about what they are. For the reason that it's easier to know and understand something if it's named for what it is or what it looks like. And second, a lot of those names come from early doctors and anatomical scientists, I'll call it. Generally a bunch of white men, often doing things in a way that wasn't very cool. We're doing, you know, what's the word I'm looking for? Thank you, unethical, and even stronger than that, like unsanctioned. What's the word for you to do something to somebody that they didn't actually want you to do? What I can't think of it. There's a specific word here. Play the word game with me. They did bad shit to people, and then they named parts of the body after the stuff that they found out. Okay, I'll just say that there's a specific term I'm trying to get at here. It has to do with unethical. I can't come up with it, but you get what I say, right? Okay, cool. Man, it's Friday. Where's the vocabulary? Okay, let's talk a little more about this. Oops, I didn't mean to do that. Apologies. Let's see. Yeah, I just got a couple more slides here, and then I want to get in and talk about Finney's gauge. So we have these association areas in the cerebral cortex as well that are involved with receiving sensory input from lots of different places. We have the anterior association area, the posterior association area, and the limbic association. I'm not going to talk about these in too much detail. I just want to highlight that there are these association areas and that they're bringing information together from different places. I alluded earlier to the limbic system. You see the limbic association here. That is integrating a lot of information about things like fear and emotions generally, but things like fear, happiness, anger, stuff like that. Yeah, I don't need to worry about that slide. Okay, so what I want to highlight here is I'm talking about how all of these different parts of the brain do different things, right? Now, they're all integrated, of course, but what this highlights is actually the way that we used to know what those different parts of the brain did is because people would be injured in certain ways and damage certain parts of their brain, and then certain things wouldn't function, and we'd say, oh, that thing that's broken must control this part of our body. And so an interesting case study, you probably heard of this guy, Phineas Gage. He lost functioning in much of his prefrontal cortex when he was 25, when he was working in a railroad, and there was like an explosion and this metal rod went through his head. And you can see where it entered and exited his head here. Absolutely remarkable that that happened and he survived. But what's noteworthy is that it really changed him. And they said he was formerly capable, balanced, and shrewd. He became incapable of making decisions, irreverent, fitful, and grossly profane. Because that prefrontal cortex is the area that controls your executive functioning, your planning, your, let's say, metered response emotionally, he just kind of lost a lot of that. And so I want to just show you this short video. It's about 5 minutes long that talks about this a little bit as a case study. And for the recording, I'm going to pause it here, but I'll provide. What I think is most interesting about that story is they talk about how over time he kind of started to get his personality back. So that suggests that that part of his brain was healing itself and kind of rewiring itself to get back to where he was before. So just a fascinating case study and kind of highlights how certain areas of the brain are involved with specific tasks. I'm just looking here and seeing what I want to cover. Oh, this is great, actually. I have like 3 more slides I want to cover today and we'll wrap up. Perfect. So I mentioned briefly, I mentioned briefly the association areas. We have this anterior association here, this part of the frontal lobe. So this is where Phineas Gage primarily had his injury. I love the fact that they describe like half a teacup full of his brain coming out. Just that unit, we should use that unit of measure all the time. I guess we still use like teaspoons and tablespoons, right? So what's interesting here is this is where you store short-term memory, so like less than 30 seconds or so. So it's your kind of like working memory, they call it, and that is involved with both visual and auditory processes. And also, as we said, this is the executive area where you're making those kind of higher order decisions about yourself. It's kind of the seat of your personality. The last association area I want to cover is your limbic association area. As I mentioned earlier, this is involved with memory and emotions, but also is integrating sensory input and motor behaviors as well. And so you're kind of processing information and has a little bit to do with how you're responding to it, and especially in relation to emotional responses and the formation of longer term memories. That is your whirlwind tour of the cortex of the cerebrum. On next week, we will get into, oh shoot, I didn't mean to do that. I want to talk a little bit more about how these areas are connected, and then we'll get into the protective layers of the skull. One last point I want to talk about is lateralization. So lateralization has to do with left and right side. And we talked about, for example, contralateral sensory and motory cortices. What's interesting is that our hemispheres are also specialized in certain tasks or certain ways of approaching tasks. And so generally speaking, your left cerebral hemisphere has more to do with controlling language, math, and logic. And the right hemisphere is more involved with things like creativity, emotion, intuition, artistic and musical skills, etc. Now, in about somewhere around 5 to 10% of the population, this is switched. And so it's not always the case, but interestingly enough, it's most often the case like this. And of course, this has to do with being left or right-handed as well. Almost everyone is either left or right-handed. A very, very small proportion of people are truly ambidextrous and can do anything with their left and their right hands. But whether or not you're left or right-handed also ties into kind of which of your hemispheres can be considered more dominant. So it's often said that people that are left-handed are a bit more creative because that left-handedness is tied to the right cerebral hemisphere, which is more involved. That's actually perfect timing for what I wanted to cover today. Any questions about that? It was yeah, today was a little bit of a whirlwind. Oh, you saw brain cells playing Pong, and that's cool. All right, I want to just wrap things up today. I don't have a ticket out. I just have some general information. First, I want to debrief lecture exam number 2, which you did earlier in this week. Once again, those open book exams, the class is doing great. The class average was just under 92%. You can see a histogram of scores here. A lot of you are getting right, between the 85 to 95 range. A few of you knocked it out of the park. I had two 100s on the exam, and a few people on the tail end here. If you are on this tail end here, think about how you approach this exam. Think about what support you might need for the last exam and what you can do differently. These exams being open book seems like it's a great place for everyone to get a lot of points and kind of boost up their average. If you compare that class average of 92 here to the lab practical, for example, where the class average, I think was, I don't remember exactly, it was around 70 or so. So pretty significant difference there. And so in a way, this is a good chance to balance out your score in the class. Any questions or concerns about exam 2? I just went straight up multiple choice for that one too. I was like, heck, just do that. Nobody really seems to complain about that. All right, on that note, your next, I want to remind you, you've got 2 tutoring sessions. Oh, I didn't put it here, but I do have open hours on Monday as well from noon to 2 in my office, or no, in the lab room, sorry. And then you will have a quiz next week, a week from today. This will cover the brain and will be a closed book exam, similar in format to previous closed book quiz, excuse me, Similar in form to previous quizzes, there's details about this in your class program for Monday. But it will cover the brain, basically everything on the brain, because the brain was not on your exam. And we'll finish up the brain on Monday, so I'll have plenty of time to get ready for Friday next week. Otherwise, I've got your Friday. Oh, no, go ahead, hon. Okay, I've got your Friday Venn diagram. This one's only mildly amusing, but it's all I could come up with this week. Have a great weekend, everyone, and I'll see you Monday morning.